Let's see. Also, if you'd like to ask the speaker a question, we would ask you to please we'll ask the speaker to please repeat the questions so that for the benefit of the online audience. And as you may have noticed, we're starting 5 minutes later this semester than we have in the past, and that's because there's a class in here up until just before noon, and it takes our staff, some time to get everything set up for properly executing the seminar. So in the future, you can probably take a few more minutes to enjoy your pizza and soft drinks and start filing in here around 1/4 and we'll be ready to go by 20 past. So I don't know, we're live. Okay. So the last announcement on my list regarding these housekeeping items concerns our online attendees as well as those of you here, and that is if you'd like to receive PDHs for your participation in the seminar today, just be sure that you send an email to LB Fry at the address that's on the seminar announcement. And if you would like to if you did not receive the announcement directly but would like to in the future, please give us your email and we'll add you to the list. And there's one change to the PDH situation. These have been reassessed, and so from here on out, you'll receive 1.5 PDHs for participation in this seminar. So just make note of that in terms of anybody who's keeping track. Oh, and let me welcome our online participants. We have representatives from the FRA, Metra, Parsons, BNSF Railway, AECOM, University of Kentucky, the Volpe Center, Patrick Engineering, TTCI, CN, Michigan Tech, IDOT, TUV Rail Sciences, Amtrak, LTK, ESI, CTA, Bowman Barrett and Associates, and Winnebago County, Illinois. So we welcome all of you. It's a very good turnout online, and we're glad to have you. And so I'll go ahead and introduce our speaker. The William W. Hay Railroad Seminar Series is sponsored by the National University Rail Center here at the University of Illinois at Urbana-Champaign. And on behalf of all of us, we thank the US DOT for their ongoing support. It's greatly appreciated by those of us here on the campus as well as those participating via the internet. Over the past decade or so, there's been broader appreciation of the importance of track support conditions to maintaining a safe and efficient railroad bed. This has become especially evident as axle loads, traffic volume, and speeds have all increased. A particularly important aspect of this is what are known as track transitions, which are locations where the support conditions suddenly change, such as when going from ordinary track onto a bridge and various other similar circumstances. Degradation of the surface geometry of these locations can become a serious problem, and our speaker today is conducting research to understand it and develop strategies to prevent or mitigate the problem. Timothy Stark completed his BS degree at the University of Delaware in 1981, his ME at UC Berkeley, and his PhD at Virginia Tech in 1987. He joined the faculty here at the Department of Civil and Environmental Engineering at the University of Illinois at Urbana-Champaign in 1991, where he is a professor specializing in geotechnical engineering. Dr. Stark has been conducting research on seismic testing for track substructure assessments and performance of track transitions for many years. This includes dynamic finite element modeling of track transitions, ballast testing and modeling, seismic surface waves to estimate ballast and subgrade moduli, and ways to non-invasively measure and characterize track performance. He has served as an investigator on over 50 research projects with railroad grants from the FRA and the AAR. Dr. Stark has authored or co-authored over 270 peer-reviewed publications from his research projects. He's an editor of the ASCE Journal of Geotechnical and Geoenvironmental Engineering, is vice chair of the ASCE Embankments, Dams, and Slopes Technical Committee. In recognition of his extensive research, teaching, and service contributions, he has also been the recipient of numerous awards. Please join me in welcoming our speaker today, Professor Timothy Stark, who will present the William Hay Railroad Engineering Seminar entitled Measuring and Modeling Differential Movement at Railroad Track Transitions.
Thanks, Chris. Good afternoon, everyone. It's a pleasure to have this opportunity to describe some of our work on track substructure. Let's see. Okay. So I'd like to first introduce my co-presenters. First is Steve Wilk, a PhD student here at the University of Illinois. Steve, stand up, raise your hand. Good. Steve's really leading this effort, both the field and modeling aspects of it. Next is Professor Jerry Rose at the University of Kentucky, who's helping us greatly with the field operations. Yang Jiang, did you make it today? No. Yang's helping us with the analysis of the video camera data, which I'll show you in just a minute. And Kangyu Fang is helping us with the numerical modeling. Here are the 5 main points I want to touch on today, and then I'm going to wrap it up with a quick summary. So first is part of what we're trying to do with the field and numerical modeling for this project is identify some of the factors that are contributing to differential movement at railroad transitions. And so some of the factors we've come up with so far: open deck bridges, wing walls, and if you look at the lower left photo here, this is sort of traditional wing walls. The wing walls or abutment walls are perpendicular to the track versus, say, parallel to the track, which you'll see in just a minute. A turn or a curve in the track, fill height, soil type of the approach embankment, fouling, poor drainage, grade crossing, which I'll illustrate in a little bit, rail joints, and finally gaps in the track system. And so that's where I'd like to start, is gaps in the track system. These can occur, say, between the rail and the tie plate, between the plate and the tie, and between the tie and the ballast. So that's where I'll start, and then we'll move to some other aspects. So we started with a tie-ballast gap, and we sort of happened onto that with the instrumentation at 6 Amtrak sites on the northeast quarter near Chester. At these sites, wheel loads and vertical displacements with depth were measured, and there are 2 sites that I want to focus in on, 1 bridge, 2 sites. It's the Upland Street Bridge and the open track site, which is about 60 feet from the approach that I'm circling, and hopefully online people can see my mouse, and the approach, which is only 15 feet from the bridge deck. So the open track site actually has more clay in the subgrade than the approach site, but it's still actually performing better than the approach. So sort of less desirable geotechnical conditions, but better performance in the open track. So let's take a look at why. So on the left is the transient displacements for the open track site that I'm pointing to, and on the right is the transient displacements with depth for the approach site. So let's focus in on the open track first. The dark blue line here is essentially the movement of the tie under an Accelerometer power car. And you can see the first wheel hitting, and then second wheel, the body of the car, third wheel, and fourth wheel. And the displacements there, transient displacements, about 0.4 of a millimeter. Now the other important thing to notice is the LVDTs at greater depths are showing a similar response as the tie. So notice there's the peak or largest displacement of the tie, and then the first LVDT and subsequent LVDTs with depth showing essentially the same response. So what that told us was we had good contact or communication between the rail, tie, ballast, sub-ballast, and subgrade, because they're kind of all responding together. Contrast that with the transition zone on the right, Upland 15, where the dark blue again is the tie, and you can see the tie is sort of moving a little bit before the wheel actually gets there or arrives. Then the tie displaces about 1.5 millimeters instead of about 0.4 millimeters, which is a very big difference. Notice the difference in the scale of those 2 vertical scales of those 2 graphs. Then the other important thing to notice is the LVDTs 2 through 5 in the approach are much different behavior than the tie. So you can see not only they're not moving as much, but they're delayed. In other words, it's taking longer time to mobilize or experience displacement in those LVDTs. So what's happening there is there's a gap under the tie. It's taking a little bit of time for the rail to push the tie down, to contact the ballast, finally contacts the ballast, puts some load into the sub-ballast. We get displacements, and then displacements and load into the subgrade. So that's how we started looking at a tie-ballast gap. Now, one other important thing to notice on the approach, Upland 15, is notice after the car passes, the dark blue line exhibits quite a bit of rebound. Right here, where this red arrow is. So basically the rail, the stiffness of the rails, pulling the tie back up out of the gap, goes basically 1 millimeter up and then kind of settles back down. And this is sort of the concept of the dancing tie. So what does that look like in real life with a video? So here's a video of a track with really good support, probably some of the best we've encountered so far. Now watch the rail and the tie in this. Loaded freight train, 25 miles per hour. You can see our accelerometer attached to the tie and two targets, one on the rail, one on the tie, which I'll talk about in just a minute. So look at that. The rail, the tie, barely moving. Real tight, good support, so when the wheel goes across, it's loading the rail, it's loading the top of the tie, loading the bottom of the tie, loading the ballast. Now, let's contrast that with poor tie support and what that might look like and sort of explain the Upland 15 data that I just showed you and the rebound of the rail. This is a commuter train. So you saw the tie go down, the rail pull it back up, and so on for the next wheel. Now there's one other thing to notice in that video. Anybody? The water. So there's the poor drainage and foul ballast that you saw on the factor slide I just showed. So that led to developing a tie-ballast gap model, which is illustrated on the left, this schematic. And so where we start is with no wheel passes. The tie is in intimate contact with the ballast. The ballast is sort of in a, I'll call it a loose condition, less than optimal density condition. And when the first wheel goes across it, which I'll show you a video in a little bit, that tie compresses the ballast, the particles rearrange, and when the rail pulls it back up, we're left with a gap on essentially the first wheel pass. And so the real question is, how large does that gap grow to be over time? And so here's our model for it. With no wheel passes, this load displacement curve, which I show right here with my mouse, starts at 0, and then with every subsequent pass we have a gap. The question is, how big is that gap? And I'll show you how we're going to measure that non-invasively in just a minute. And then we have the load displacement behavior of the ballast. You can see it's a nonlinear function from the x-axis up to a linear portion, and now we've got the tie in contact with the ballast. We've passed the seating load of the ballast, and now the ballast can start supporting some of the load. And that is essentially ends up with a linear load displacement curve, as you see there. So that's sort of the framework. So let's see what the data looks like from Upland Street. Here is the data from January 2013. The open track is the green symbols, and the approach are the red symbols. So notice that once the ballast is loaded by the tie, the ballast is showing roughly the same stiffness or load displacement after the gap's been closed. So the slope of this line is pretty close to the slope of this line, our K-mob, or our mobilized stiffness of the ballast. The big difference is that the gap, the tie-ballast gap in the open track, is only about 1/4 of a millimeter, whereas at the approach it's about 1.4 millimeters. So that 1.4 millimeters has to close before the ballast can start taking up some of the load being applied. And this gap can increase with time, as I mentioned, and so that same approach in July 2014 had a gap of 6.7 millimeters, so it grew from 1.4 to 6.7. Okay, so that looked all pretty good, except at Amtrak the cars were all heavy enough that we didn't get to define the initial portion of this ballast load displacement curve, or in other words, the nonlinear part that I'm pointing to on the screen. So you can see the power cars, those are these green dots at the top, are fairly heavy, well above the seating load. And here are the coaches, still above the seating load. So we really didn't have a way to explain this initial portion yet. That's going to be important when we start talking about repairs and design measures, because you need to predict how much the ballast is going to displace under its load, both transiently and permanently. So luckily there was some instrumentation also at Norfolk Southern, and that site experienced both loaded and unloaded cars. So the unloaded cars allowed us to define this initial portion that you see here in the red dots that I'm pointing to. So that gave us sort of the initial curve, and then up to the seating load we get another linear portion. So from that data we were able to fit an expression for the load displacement of the ballast. We tried cubic and bilinear fits, and I think the cubic fit, which is in red, looks pretty good. And so that's what we're going to use to predict the transient displacement of the ballast after, say, a repair or for a design, which I'll talk about in just a minute. Okay, so that set up tie-ballast gap for us, and the numerical modeling that Steve's doing showed that it's not just one tie, it's really what a series of ties are doing that really control what the load distribution looks like. So if we have gaps under multiple ties, as you see in this schematic, the load distribution varies considerably. So we had to find a way to measure the gap under a number of ties in a stretch of track, not just one tie. And so that led to developing some non-invasive techniques for evaluating gaps in the track structure. So that's part two of my presentation, developing non-invasive instrumentation. So at this point we're focused in on accelerometers and high-speed video cameras. So the accelerometers give us an idea of the tie acceleration, and we can also use that and Newton's second law, F equals ma, to estimate what the applied loads are from the accelerations. So the accelerometer is sort of giving us the heartbeat of the track or pulse of the track, and high-speed video cameras giving us actual rail and tie displacements during the loading. So we've investigated 10 sites so far, and this has been great because we have a range of good to poor support from these 10 sites. So here's one particular setup in the left there. Steve Wilk is here in the background. He's operating the accelerometer data acquisition system as well. There's a video camera right next to him right here. And Professor Rose is here in the foreground operating a high-speed camera, sitting on an ASTM-approved bucket there, I'm sure of it. And he's got that camera ready to go. And on the right is the accelerometer we're using on the tie. A drop of super glue attaches the accelerometer to the tie, and we're all set. Also, you can see targets on the rail and the tie, and actually now we're putting targets on top of the tie, so we don't have to move any ballast as well. So let's see what we get from this. So I'll start with accelerometers. I'll take you back to Chester and the Amtrak Upland Street Bridge site. So notice the tie where the red arrow is. And this is a video of that tie. And there's an accelerometer on the end of that tie. So you can see the tie moving extremely rapidly, accelerometer measuring the accelerations of the tie. The response of that tie, the time history, is the red lines in the graph on the left that I'm pointing to. The green is the accelerometer under the same train at the open track tie. So the green is sort of good support, and the red is poor support in the approach. You can see much greater accelerations in the approach zone than the open track, about 30 G type of acceleration in the approach versus 5 G in the open track. And so based on looking at a number of sites, we think if the acceleration is less than 5 G, that's a good indication of good tie support. As I mentioned, we can use Newton's, or we're trying to use Newton's second law, F equals ma, to now predict the applied forces from the acceleration data. Now we can convert the time history to the frequency domain, and that's shown on the right graph here. And that really helps illustrate the behavior of the tie. The frequency domain, you can see, shows an extremely high amplitude at a frequency of about 100 to 120 hertz for the approach right here, and fairly high amplitudes thereafter to about 200 hertz. And contrast that with the open track that shows very little amplitude throughout a full range of frequencies. So we think utilizing the frequency domain is going to be a quicker way to assess track performance from the accelerometers. So now let's shift gears to high-speed video cameras, and a site in which we've used both accelerometers and high-speed video cameras, but this site's really lent itself to high-speed video cameras. So we have 8 accelerometers. We generally install 8 accelerometers at a site, and you can see them from 1 on the bridge deck to 8 out here where my pointer is. 2 video cameras, 1 on accelerometer 2 and 1 on accelerometer 3. And now you'll see that accelerometer 2 and 3 have very different behavior, even though they're fairly close together. They're only 3 ties apart, but you're going to see a very significant rail tie gap at number 2 and a significant tie-ballast gap at accelerometer number 3. We'll also show you the effects of a centerbound tie, the effects of air tamping, and also the effects of 2 transitions close together at this site. So this was really a good site. Here's a grade crossing that I'm pointing to on the left, and of course an open deck bridge on the right. So this really was a good site for us. So here's a video. The video starts at accelerometer 2, and then I'm going to turn to the left 3 ties, and you're going to see accelerometer 3. Now, be sure to notice the difference in behavior between accelerometer 2, which is on the screen, and what you'll see at accelerometer 3. Pretty significant rail gap. Still a little rail gap, but now the tie, you see a tie-ballast gap, just 3 ties away. Okay? So let's take a little in-depth look at the results from the video cameras and accelerometers on those. So I'll start at accelerometer 2 and where video camera 2 is. Here is a plot of vertical displacement from the video camera. Blue is the rail, orange is the tie. So as you saw in the video, quite a significant rail tie gap. And if you look at the time history, you see a displacement of about 4/10 of an inch between the bottom of the rail and the plate. And I'll have ground truth for that in just a minute. Now, because there was such a large rail tie gap, notice the tie doesn't move very much. There's such a big gap that the tie is really not feeling much load or moving much. So here's a photograph of the rail tie gap. That's my finger, and you can see it's about 4/10 of an inch not an inch? Inch, not millimeters, which is in good agreement with the time history. And so here we expanded the time history from 20 to 22 seconds. And so the blue line is the rail moving about 4/10 of an inch, closing the gap, and just moving the tie just a little bit, as you saw in the video. A little bit of rebound of the rail as it's coming back off the tie, and then back down for the next wheel load. All right, so now let's shift to accelerometer 3 and camera 3. Totally opposite, because you saw in the video there was a fairly small rail tie gap, but a much larger tie ballast gap. So the orange is now the tie moving, the rail is the blue, and so the rail is deflecting now only about 2/10 of an inch, and the tie is now moving about 1/4 of an inch, right, because we've changed the gaps. Now, this is about 20 feet from the bridge deck, and accelerometer 2 is 14 feet. So we can zoom in on the accelerometers now and compare that to the video camera. And actually, I'm going to talk about the tie first. So we have a target on the rail and the end of the tie. And so this led us to think that this tie is center bound, because notice that the tie is the orange is moving more than the rail. So the end of the tie is moving more than the rail, so it's bound in the middle, and it's sort of like cantilevered, and the end moving more than the rail. I'm going to come back to this center-bound tie in just a minute and show you the accelerometer on the other end, number 4 right here, and you'll see 3 and 4 move about the same, and essentially the middle is fixed, so a center-bound tie. Okay, so let me summarize accelerometer 2 and 3. At accelerometer 2, 14 feet from the bridge, you can see a significant rail gap here and very little tie movement. You move 6 feet away and you have a significant or a greater tie movement than you do a rail tie gap. So both gaps playing into the performance of the track. Okay, so here's the accelerometers from 2 and 3. Number 2 is on the left, and accelerometer 3 is on the right. So notice accelerometer 2 is only showing about 10 G. Remember, the tie wasn't moving very much, but it's still greater than 5. 5 sort of our cutoff between good support and bad support. So it's still poorly supported tie, but it's still moving a little bit, but not as much as 3, where now you're seeing accelerations of 20 G. We can use these acceleration time histories and double integrate them to get a displacement time history. And now we can compare the video camera displacements to the accelerometer-derived displacements and check our accuracy. So let's do accelerometer 2 and camera 2. So this top graph is the video camera displacement of the tie. You can see about 6/100ths of an inch tie displacement. And if you doubly integrate the acceleration time history, it's about 5/100ths of an inch. So pretty good agreement. Let me shift over to accelerometer 3. We have about 1/4 of an inch to 3/10ths of an inch from the video camera, and the accelerometer giving us about 2/10ths to 1/4 of an inch of tie displacement. Again, within pretty good agreement between whether we measure the displacement via camera or we measure it via accelerometer. Okay, so let me go back to that Centerbound tie. I mentioned we had an accelerometer at the other end of the tie, which is number 4. And so you can see we have accelerations on one end and the acceleration on the other end. And you can see that 3 and 4 are basically giving us about the same response. So the ends of the tie are sort of going up and down, and the middle's fixed, giving us indication that that's a center-bound tie. And so we can look at things like that with the accelerometers and video cameras. We hope to get back to this site, and we'll put a accelerometer at the middle of the tie right here and hopefully confirm that that's a center-bound tie. Another interesting thing is, notice that the accelerometer 4 experienced more wheel flats. Look at all these spikes up here. These are all wheel flats. Than the accelerometer on the other side of the tie. So the wheel flats aren't equal on both sides. Both of the ties, or both of the accelerometers, still exhibiting 20 G of acceleration. So again, both ends of the tie not well supported. Okay, so that's all the good news. The even better news is, on one of our visits to the site, the next day, the railroad air tamped this stretch of track. So, start of the second day, they air tamped, say, from roughly just in front of that grade crossing to the bridge deck. And so we were able to measure the first wheel across the air tamped accelerometer 2. So this is accelerometer 2. This is the first wheel. This is accelerometer tie 2. First axle across this tie. So watch carefully the tie move and the ballast. So remember, I started with the tie-ballast gap. The tie is in contact with the ballast. The first load rearranges the ballast particles. The rail pulls it back up, and we start the gap formation. There it is, right after the first axle after air tamping. So let's look at the displacement time history here on the right. And this first valley right here is the first axle. So the rail goes down approximately an inch. Comes back up, goes back down, comes up a little bit, goes back up. So we start with an inch. We go up to about 1/4 of an inch. So there was an inch of transient. After the first axle, we've already had 1/4 of an inch of permanent displacement. Now let's look at the tie. The tie is the orange line. So it initially goes down about 3/4 of an inch. Comes back up to 1/2 an inch. So on that first wheel pass, we've had about 1/4 of an inch. So there's the start of our gap, 1/4 of an inch. By the end of this little stretch, we have the rail at 4/10 of an inch permanent displacement and the tie at 6/10 of an inch. First train across it. So let's move to the 6th train across after air tamping. So on the left is the graph before air tamping, so pre-tamping. I showed you this one earlier, the rail moving about 4/10 of an inch and the tie moving considerably less than that. So by the 6th train after tamping, the rail is now moving about 3/10 of an inch, so a little better, and the tie still moving about the same, because again we have a fairly large tie rail gap, so the tie is not being loaded significantly yet. So this was really a nice exercise, because we could start evaluating the effect of remedial measures, which you'll see in just a minute. Okay, another nice feature of this site is it happens to have 2 transitions, a grade crossing and the open deck bridge Here's the grade crossing in the foreground that I'm pointing to, and then here's the open deck bridge. Or looking backwards on the open deck bridge, looking to the grade crossing. And so this has resulted in some pretty interesting behavior coming off of a transition. So the grade crossing 66 feet south of the bridge. All right, so let's start with the the southbound train is blue, the red is the northbound train. So accelerometer 8 is right here, 51 feet from the bridge deck, and accelerometer 7 is 36 feet from the bridge deck. So the train is coming off the deck. It's going to hit 7 first, and then it's going to hit accelerometer 8 second. So notice accelerometer 7 is showing considerable load. And look at these accelerations, like 100 to 150 G. Because the trains come off the bridge, it's sort of galloping or hopping. It's hitting right around accelerometer 7. But by accelerometer 8, notice very little acceleration, so it's kind of popped back up. We can do the same with a train heading northbound coming off the grade crossing. So it hits accelerometer 8 first that I'm pointing to. Considerable load. Look at some of these accelerations now up around 200 G. But by accelerometer 7, much lower load or lower accelerations. Then an interesting point, notice that in between here there's a lightly loaded or empty car. And you can see it gives a different response at 8, a loaded car versus an empty car, from accelerometer 7 to 8. All right, so I think the future direction for our non-invasive monitoring is we want to now install a permanent installation, and then that will allow us to look at environmental and seasonal changes, the effect of rainfall, precipitation on, say, fouled ballast or other aspects of the track structure. We would house most of this in a wayside box that you see right there. Okay. Oh, yeah, Chris?
If the questions I'm going to ask are something you're going to address coming up, just tell me and I'll wait up. But could you go back to the 2 slides back, please? So this business about the empty car seeming to have lower accelerations at site 7 versus the opposite at site 8. Is that something you're going to explain to us later?
The question is,
very interesting.
Yeah, it is. The question is, back to accelerometer 7, notice that we think that this is or at least a less loaded car hitting 7, because you can see the accelerations around it, say 100 to 150, versus over here at 8. So we concluded that from the difference in signatures.
Well, I'm actually noticing that some of your other peaks are almost inversely. So look at just below 30. You have a little low spot on 7, and there's a high spot on 8.
Oh, right here.
Yeah.
Yeah.
Is there something going on here?
It might be maybe a single car. Maybe this is a few lightly loaded cars.
Okay.
Right.
And just one other question. Several slides we went back, and you don't have to go back, but I noticed you had tank cars on there. I didn't know what that was about.
Yeah, I know where that is. So this is back. This is back to the Centerbound Tie, and we had accelerometer 4. We recorded that these time histories or acceleration peaks corresponded to tank cars, and they were a little higher. So we've, if you're a tank car person, maybe you can help us out with that. But we were thinking that basically the fluid in the tank car may be moving a little bit and giving us a little higher acceleration. But those being tank cars versus, say, the box cars that were in front of it.
Okay. It'd be interesting to know if that was a consistent pattern or it just happened once and you noticed it.
Have we seen?
Well, with the trains going opposite way, it was what you found out. It was pretty consistent where it's larger at one location, not the other, and what I'm guessing is that if you have a heavy train, it's going to bounce almost at a different rate than that lightly loaded. So if it's lightly loaded, it's not hitting accelerometer 7 as much, so that's why you see the lower acceleration. But then it's bouncing, it's accelerometer 8 more, so therefore you see the higher ones. And that's
some kind of different harmonic.
yeah, that'd be my guess.
I assume it's very significantly train speed.
With train speed, we do see the differences. Those two trains, we tried to get around the same speed, so we're as much as we can apples to apples, but can't control everything. But those are similar spots.
Your first frequency domain shot there, where you identify those peaks, and it gives you a great idea of how fast the train's traveling, right?
That actually is like high vibration, and
Yeah.
you can pick that out, but a lot of it depends on timber, concrete.
Oh, okay.
Not a very good mic man.
Okay, are we good on train direction? All right. So that takes me to the third point of the presentation, design and repair measures. So I've been working on highway bridges since the 90s, a study with IDOT on highway bridges. And they're somewhat complicated, but I find those much less complicated than railroad bridges. So for example, on the left is the replacement bridge south of Minneapolis. The existing bridge is similar to the I-35 bridge that collapsed. And so MDOT said we ought to take this one out too and put a new one. Very soft, compressible approach. And so we overcame, or at least so far we've overcome the soft approach with a geosynthetic reinforced load transfer platform supported on pipe piles, which you see on the left photograph. And then on top of the load transfer platform, lightweight fill, geofoam to form the embankment, and then a pavement to distribute the load. And so far so good with this highway bridge approach, complicated site. But for railroad bridges, I'm finding it's more complicated, more complex problem. And so what we tried to do was try to simplify this complex problem. How do we boil down all the different sources of displacement, both transient and permanent, that can occur, so we can assess whether our design or remedial measure will be effective? So we tried to get away from complicated things like calling something a banana when you can obviously call it curved yellow fruit, and make it really simple. And hopefully somebody enjoyed a piece of curved yellow fruit for lunch today. So here's what we came up with. It's a transition zone scorecard. And we welcome comments on this, because maybe this isn't as simple as yellow curved fruit, but here's our attempt. So we tried to summarize all the sources of both transient and permanent displacement in the approach and on the bridge, or the transition and the bridge. So T is the transition, B is the bridge. And look at all the sources: rail compression, rail tie gap, which I just showed you a video of, tie pad or plate displacement, tie displacement, tie-ballast gap, which I illustrated with video, ballast displacement, and that we got our arms around that with a cubic function, sub-ballast displacement, subgrade displacement, and lateral displacement if it happens to be a curve. So we're trying to use accelerometers and video cameras to come up with values of these particular displacements. So at the end, you see the bottom line here where I'm pointing is total. We want these two totals in the transition and the bridge, both transient and permanent, to be equal. And if they are equal, we have no differential movement, we have no bump at the beginning or the end of the bridge. So let's see how this works. I started the show with an open deck bridge, so let's go back to that. There it is on the left. Obviously it's undergone some differential movement. And why is that? So if we look at the transient displacements, the rail compresses essentially the same in the transition versus the bridge. It's the rail. There is a rail tie gap in the transition. There isn't on the bridge. So there's our first source of differential movement. We'll say the tie plate has the same displacement on the transition as the bridge. Timber ties both on the deck and in the transition, so we'll make those equal. And then we have this whole source of transient displacements in the transition, the tie-ballast gap, the ballast displacement, sub-ballast, subgrade, and this particular site has a turn. So we get displacements there, but of course none on the bridge. And so there's our source of differential movement. Transiently, and then you can see similarly permanently. So that leads to the differential movement that's shown in that photo. So let's try another example. How about a well-performing bridge? Because not all transitions are problematic. And here's an example of a well-performing bridge transition. The design attributes here include a ballasted deck, an HMA underlayment under the ballast, consolidated fill. If you look closely, this bridge approach has a compacted fill of about 60, maybe 70 feet high. So this would be a great example where you would expect to see differential movement at the transition. But before the track was placed into service, the fill was allowed to essentially come to equilibrium for a couple of years before track placement, so it removed some of the subgrade displacement that would have occurred if the track had been built immediately. Another important design feature, notice the concrete wing walls. The concrete wing walls are parallel to the track, right here, and they're providing some nice confinement to the ballast, so the ballast isn't spreading out under the load. It's keeping it tight and formed up. So here we go, rail compression the same in the transition to bridge, tie plate the same, tie displacement the same because it's timber on the transition and the deck. Ballast displacement the same, both transiently and permanently. There's no tie-ballast gap on the deck or the transition. I talked about the sub-ballast being confined by the wing walls, the subgrade undergoing consolidation or deformation before the track being constructed. And finally, notice the track is perfectly straight, not a turn. So here we end up with essentially equal transient and permanent displacement, and this track's been performing well for several years. This is the cubic function I showed you earlier, and so we're using this to predict what the transient displacement of the transient and permanent displacement of the ballast, and so we can match it up in our scorecard as you see there. Okay, so let me shift gears to numerical modeling. And I want to start with open track, and then I'll go to the bridge approach. So here's the model in LS Dyna that we're using. This is the open track model. So we've simulated a power car or rail car with this little cart. Here's the actual rail modeled exactly and the wheel on top. And now in this model we can put gaps under these ties. We can have multiple ties with gaps, multiple ties with gaps, and we can vary the thickness or the height of these gaps. And so here's a video of a tie with a gap and the wheel coming across it. The gap closes, the tie loads up the ballast below, and now we can study the effect of load distribution for different thicknesses or heights of gap. And that's kind of illustrated here. This is the load redistribution without gaps, and then I'll look at with gaps. So the wheel's above tie 19. So if I come in at 0.46 seconds, notice tie 19 right here is carrying about 40% of the wheel load. Same time, notice that tie 18 and 20, which is the blue and red right there, is about 22. We just use 20, even though it's a little higher, so we go 40, 20, 10. And then if we use the outer ties, 17 and 21, which cross right here, that's about 10. So if there are no gaps, the wheel load distribution is roughly 40, 20, 10. So keep that in mind as we put gaps in the system. So now let's go and put some gaps in that same stretch of track in our numerical model. We'll focus in on tie 19, but then we'll put gaps under 18 and 20. So let me start with tie 19. So if there's zero gap under tie 19, look, it's feeling 40% of the wheel load. As we increase the gap under tie 19 to a quarter to a half to 3/4 to 1, notice that tie starts shedding that 40% to the adjacent ties. And those start getting overloaded. And they start developing bigger gaps and so on and so forth. So let's keep going here. So now I have zero gap under 19, and now I'm going to put a gap under 18 and 20. So you can see I go from a quarter up to 1. Now look at tie 19, it goes from only carrying 40% to over 70%. So the gaps under these ties have a big effect on load redistribution. And so measuring these gaps and understanding them is really important for the load redistribution. So I focused in on 1 millimeter. Chris hasn't asked me a question yet about 1 millimeter, so I'm going to beat him to it. 1 millimeter we found is fairly significant, even though, and that's still surprising to us, it's really small, 1 millimeter. You know, it's 1 millimeter. But notice we drop from 40% down to 0 with 1 millimeter. Really small gap, and we shed the load. So from Amtrak, the sites that have been performing well have a gap less than 1 millimeter. The two approaches that have not been performing well have a gap greater than 1 millimeter. So that sort of helped us rationalize our numerical modeling. In addition, Seelig and Water present some laboratory box tests that show significantly more settlement when you have a gap below the tie greater than 1 millimeter as well. You can see considerably more settlement. So the takeaway of that is fairly small gaps. The tie has to move a lot. The rail starts bending. The rail has a high stiffness, and it starts shedding the load to adjacent ties very quickly. Okay, so that was open track. We're also looking at the bridge approach. So here's the same model with the Upland Street Bridge approach accurately modeled, and our power car running across the transition and onto the deck. And so we've measured the beams. This is the underside of the Upland Street Bridge in the lower photograph. And we have the big retaining wall. If you look closely, this pink area right here is this massive masonry wall that's there in the approach. So let's look at the results of the approach now in the numerical model. So here's the cart rolling across. The approach is on the left. Here's the start of the bridge deck where my mouse is to the right. And even if we have no gaps and the rail is flush from the transition to the deck, perfectly flush, we'll still get a bump or a dip at the bridge, because as the car is coming towards the bridge, we're getting transient displacement of the ballast, the subgrade, the subballast, and that's leading to this dip right here. So even if the rail's flush, we'll still get some transient displacements, and now what happens, the front wheel bumps into the deck. It's causing an impact load, and that'll also cause the back wheel to drop a little bit, and you can see that in our numerical results. So the blue and red right here is the front wheel hitting the deck, and then the back, the green and the purple, which I'll zoom up in just a minute, are the back wheels that are also being pushed down when the front wheel hits the deck, like this, and so I'm going to blow that up right there. So the red and blue, there's the front wheel hitting the deck, and there's the back two wheels being pushed down as the front wheel rolls onto the deck due to transient displacements, not permanent. Here's the similar results, but as a function of distance. So notice that the back wheels are going down about 10 feet from the bridge deck. So the wheels hitting the front, the wheels are being pushed down roughly about 10 feet, so that's a place or a zone in the transition that you should expect some bigger gaps in the track system due to the increased load. Now, that model was all with no gaps. If we now put gaps under those ties, the impact loads and load amplification are even bigger. As you see over here, you can get about a 200% increase in the tie ballast load when we start putting gaps into the system. So it's really an important and dynamic problem there at the bridge transition, even if you don't have gaps in the drop of the rail. So here is the model extended to look at the exit of the approach. So there it's rolling on and rolling off. And like you saw with the accelerometers, northbound and southbound, you saw different behaviors coming off the approach from either direction that I showed you. Okay.
Tim,
Yep.
your theoretical cart is 10 feet wheel spacing?
9 feet, 4 inches.
Okay, close enough. All right, thanks.
Yep. How am I doing, Chris?
You're fine.
Okay, about 5 minutes?
Yeah.
Okay. All right, so let me wrap up with the last area that I have time to talk about, substructure modulus. And I mentioned the ballast underneath the tie, trying to get a handle on the modulus of the ballast, how stiff it is it stiff enough to take the applied wheel load, and so on. So we're trying to measure that stiffness using seismic waves or surface waves, and we're trying to modify a portable pavement device for railroad applications, which is pictured here. And I'll explain how this device works and how we think we might be able to adapt it to railroads. Let me go to this diagram at the top. And the cylinder that I'm pointing to is an energy source. So there's a little anvil in that cylinder. It drops. When it hits, it creates a little seismic wave that goes through the ballast, and it arrives at this first sensor that I'm pointing to. And the time it takes for that wave to get to the first sensor, we can use to calculate the shear wave velocity, time and distance. Then the third cylinder that I'm pointing to is a second sensor, and that measures the second arrival time. It's at a longer distance. And because it's at a longer distance, that wave is now experiencing a deeper depth of the ballast. Okay? So in general, if this second sensor is, I'll make up a number, 36 inches away from the energy source, we're looking 36 inches down into the substructure, non-invasively. So what we want to do eventually is, you can see it spanning one tie. We want to put this so it expands and spans 2 ties, and the energy source is in the next crib. And that'll give us a way to measure the modulus under 2 adjacent ties. And we can measure the modulus, say, at the end of the tie, the middle of the tie, the other end. And now we'll have a profile of modulus from one end of the tie to the other for modeling purposes. Okay, and here's the concept. If we go back to our tie-ballast gap, initially with no wheel passes, we could measure our modulus here under the tie, see if it's going to be sufficient for the applied loads that we anticipate. If not, we have to compact it or make it denser to hold whatever loads we're predicting, so we don't get a tie-ballast gap, or significant tie-ballast gap developing. Again, depending on the spacing of the sensors, we can look as deep into the subgrade or not. Also, we can look at the effect of fouling, which I'll demonstrate in the next slide. So we've used this at several sites. I'm going to use some data from TTCI's track. And this was very interesting because the lower photograph on the left here is actually a heavily fouled site, and the one on the right is actually a clean ballast site. So in both cases, TTCI was able to mobilize the fire department, thanks to Colin Basie, and the fire service came out and wetted both areas up for us so we could evaluate modulus before wetting and after wetting. So on the clean ballast site, you can see that the modulus, and this is the Young's modulus of the ballast, not the track, of the ballast, is 30 to 40 KSI. Now, the interesting aspect is the fouled area. Dry, it exhibited a high Young's modulus, 50 to 55, and that's because the dry soil particles or fouling particles filling up the void space of the ballast particles, giving us a stiffer mass. But when it's wetted, that modulus dropping by almost a half to 20 to 25 KSI. So we're hoping to use this device, modify it, and use it to look at ballast modulus and relate that to track performance. Now, we've correlated that with the modulus Steve's estimated using FLAC at Upland 60. You can see with rainfall in January 2015, he predicted modulus about 29 KSI, pretty similar to the TTCI test. And then in June 2015, a little drier, about 55 KSI, which is in pretty good agreement with dry fouled ballast. But I think the main issue there is the fouling material, fairly good modulus dry, but when we soak it up, it loses some of its stiffness. And that's why we're looking to install a permanent installation of these accelerometers and video cameras to look at the change in track and modulus with environmental conditions. Okay, one interesting offshoot of this seismic testing has been we need to get a handle on what the waveform of the tie looks like, whether it's timber or concrete. So we know which wave is actually the seismic wave coming under the tie, going through the ballast and coming out the other side, and we use that waveform to measure modulus. So we quickly measure the modulus and waveform of the tie, and so we're thinking this might be a way also to investigate tie integrity as we move forward with this device. Okay, so to wrap this up, differential, transient, and permanent displacements lead to the differential movement at bridge transitions. I think it's important that you have to account for all transient and permanent displacements in the bridge repair and the design. We came up with a scorecard to do that. Hopefully that simplifies it like yellow curved fruit for everybody, and hopefully that can guide some of the repair and design processes. Poor track support, generally we see that with accelerations greater than 5G. Higher rail and tie displacements, that leads to load redistribution among adjacent ties and can lead to significant impact loads at the bridge approach, as you saw from the numerical modeling. We hope to establish a permanent site where we can look at these effects with time and environmental conditions. Finally, our ballast seismic property analyzer, hopefully we can modify that to encompass two ties and measure ballast modulus, the effect of fouling, and also tie integrity. So with that, I think I'll stop and try to answer any questions.
Thank you, Tim. Yeah, we have time for a few minutes for some questions. I guess I have a question. I'm not sure if some of our people from the tie team were here that could answer this, but I was interested in the distribution of loads on your ties. I'm trying to remember which slide. It was back a little ways. Did you guys notice this?
This one?
Yeah. This one, and there was another one, I think. Maybe the one before.
I think that's the...
Yeah, that's
this one.
Right there, yeah.
Okay.
So, just curious if anybody from the tie team can comment on how well this parallels your recent experience. question is, so he's asking what the spacing is.
2 feet, 2 feet spacing.
Okay, that's for REMA. The manual does not, they recommend like 50% for the fire tax. It's probably more accurate than REMA.
Okay, the response is AREMA estimates 50%, and we're at about 40, so rough agreement.
So what are your thoughts on the next steps, or maybe some solutions that the industry might potentially be able to develop or implement as a result of the work you, or the insights you've gained?
Well, let's go to the scorecard, and everybody heard that question, right?
Yeah.
So okay, so let's go back to the scorecard, and I think it's really gets back to balancing the approach versus the deck, and especially if I roll back one more slide to an open deck bridge, you can see that this is almost a recipe for a differential movement problem. The bridge moves little, if any. Okay? So I think we need to involve the bridge in the solution. Now, I'm not saying put the bridge on spread footings like has been done with highway bridges. In the 1990s, during this IDOT study, the state of Michigan at that time was the first DOT to put a bridge structure, the superstructure, on spread footings, realizing that, look, there is going to be movement of the approach, so let the bridge move a little bit. And now the FHWA for highway bridges is recommending not pile abutments, but geosynthetic reinforced abutments that'll move a little bit. Okay? So how can we do that with a railroad bridge? I think they have to remain on deep foundations, so how can we put some more X's on the bridge column in this score sheet over here, and put some more X's under transient movements for the bridge, because otherwise only the transition's moving, not the bridge. So how can we do that? Ballasted deck, because then we have a load displacement behavior that's similar from the transition to the bridge. Putting some surface on the bridge deck, such as pads, that give us a little displacement to match up with some of the displacements we're seeing in the transition. And again, the idea is at the end that the transient displacements are roughly equal to, in the transition, are roughly equal to the transient displacements on the bridge, because that's where we have to get to at the end of the day. If they're not, you get a differential movement transiently, the front wheel hits the deck, and it just sort of goes bad from there. So I don't know, that was probably too long of an answer for that. Yep.
Dr. Stark, really good presentation. By your last answer, you would say that perhaps the focus should be more on the bridge rather than the approaches. I don't know if that'll be a yes. Nevertheless, I wanted to ask regarding the approaches. I know Dr. Tutuller is working with under tie pads, and I'm wondering your opinion on that, the usage of that, on the ties that are approaching the bridge, or perhaps making it more rigid by including a slab perhaps before the bridges and trying to make it as rigid as the bridge, the approach. So I don't know if you would say better to soften it or more rigid to make it equal. Thanks.
All right, let me go to the first part of your question, or maybe it was a statement, that you only have to modify the bridge. That wasn't the last message. The message is we have to balance the transition and the bridge. So just leaving an open deck bridge like that has essentially little, if any, movement, you've got a tough order, because there's always going to be some transient displacement in the transition. Okay. Second piece was tie pads. Okay, so tie pads in the approach, they're still going to give you movement. So how are you going to balance that movement? That's the question. Because at the end of the day, if you have a different amount of movement in the approach than the bridge, you have a bump.
Just the bridge is with clearance. That's why I've been in Upland. Upland Street has low clearance. So kind of complicated. For example, a solution with balance.
Oh, okay. So the question is, this gentleman's been to the Upland Street Bridge. He says there's low clearance between the street and the bottom of the bridge. Correct. So that's pretty well fixed. So you have to do something on top of the deck, such as, you know, on the deck is where we put, say, the pad. And we're looking at that. That has a load displacement behavior that can cover up some of the X's in the transition zone. Because again, at the end, we want to have the bridge and the approach being at the same level. So I'm not suggesting, you know, lower the deck to build it up, but there are other things you can do to the deck.
Professor, thank you for your excellent presentation. I just want to follow Chris' question. You showed the vertical load distribution on different ties. Do you have a comment on the lateral force distribution on different ties? And whether there's a gap or not between the ballast and the tie, would that change the lateral load distribution?
Yeah, and so you're talking about this graph back, the one with the open track gap?
When I go back.
Back?
Yeah, forward 2 slides. Yeah, this one.
Okay. So is there lateral restraint?
Everything we pretty much focus on is vertical movement.
It's vertical.
Calibrated, so we focused on that. We started off with LV beats, and most we just go up and down. So we really haven't gotten to lateral movement at this point. But we've always focused on straight track, where it could be too much.
Yeah, because I saw the model looks very comprehensive. You have like wheel and rail contact. So
Yep.
I was assuming there was some lateral force induced by the moving wheel. So, but yeah, as I said, we probably can look in further.
Yeah.
Thanks.
No, and so if we go back to the video of the model, Upland Street, it's essentially a straight track across the bridge. And remember, the first photograph, open deck bridge, no wing walls, and a turn, giving substantial differential movement. So right now, we just looked at straight track. Yeah,
Yeah.
Conrad.
I thought I mean, I think you hit the nail on the head when you said it's balancing the displacements of the bridge and the track, and how do you achieve that? And you mentioned ballast deck bridge, which might be an obvious choice, but in this particular case, because you have so many Upland Streets just not there by itself, there's a series of them so closely spaced that you can't just convert one to a ballast deck without affecting everything else around it. But in reference to the pads on the bridge, in fact, Dr. Kerr from Delaware did that, and I don't know if it was Upland, but it was one of the streets here in Chester back in the, I want to say, mid-90s. And the pads were in there for a while. They seemed to perform all right, but they didn't have the instrumentation that you have now to really quantitatively evaluate them. So it might be interesting to look at his approach and get the results from what he did and see how we can apply it today.
Yeah, I agree, Conrad, and we're familiar with Professor Kerr's attempt there. And I think what we could bring to the table there is the load displacement behavior, because again, we have to balance the transition to the bridge. So we have to have a pad that simulates all the displacements that will still occur in the transition, but are not going to occur in the bridge. And I think Professor Kerr, I forget what pad he used, but it was just sort of like it was almost like a damping pad, more so for vibration. whereas I would try to, and that was why that cubic expression was so important, because if we can model that load displacement, now we can take the amount of that displacement and say, okay, the pad has to cover that, that, and that.
Right, and I think part of the problem was the durability of the materials that were used, but a lot has changed in that regard in 20 years since it was last done. So.
Right, I agree. I agree.
Any more questions? So I have one sort of academic question. So
Please.
I didn't realize until I was preparing for this seminar, preparing your announcement for the seminar, that you're a Delaware grad. Did you have the good fortune of taking a class with Professor Kerr?
I did have the great fortune of having structural analysis with Professor Kerr, and so I was absolutely familiar with his tie pads and his work with Amtrak, absolutely.
So your railroad roots are deeper than I thought, so good.
Well, there you go. So, see, it's worth attending, Chris.
Absolutely. So anyway, oh, we have one question online. Hang on a second. Where is it? Can you point to it? No. So the question from online is, it sounds like you might recommend making the bridge match the track while the approach slab transitions between the two. How should approach slab transitions be used? Most transit agencies want them for a transition of modulus.
I think the question's asking about an approach slab.
Yes.
Okay. Well, the approach slab, a lot of work's been done with using approach slabs in highway bridges. And the result of that hasn't been all that successful. Basically, the approach slab, so the deck's here, and so you have, say, a concrete slab that bridges from the deck out some distance, X, and that distance can be short or it can be fairly long. But in highway bridges, essentially it transmits the differential movement to the end of the approach slab. So they haven't been that effective, in my opinion, in highway bridges. So given the loads we're talking about and so on with track, I'm not sure that that's going to be the solution either. Because what happens at the end of the slab? We still have the transient and permanent displacements of the ballast, the sub-ballast, the subgrade. You know, just go back to the scorecard. You're just moving that scorecard from the deck to the end of the slab. If you can balance it at the end of the slab, I think it's fine.
What about a progressive decrease in tie space as you get closer to the bridge transition? I understand it's problematic in terms of the automated tie maintenance equipment.
The question is, what about decreased tie spacing going up to the bridge deck? That puts lower amount of stress, because instead of 40-20-10, it might be, I don't know, 30-15-5 and something else. So that's better. So that may come up or produce a smaller tie-ballast gap in the system, which can help you. But the bottom line is, even with shorter tie spacing, let's say 1.5 feet, you still have all those displacements, transient and permanent, under the tie. Now, again, they might be smaller because the load's smaller, but they're still there. Exactly.
All right, well, I think we'll suggest we wrap it up.
Okay. Thank you.